Hi, this is Bukya Krishna, roll number 20951A2130, branch Aerodynamics Engineering. So, my topic is control of boundary layer separation for lifting surfaces. First, what is a flow separation? Whenever there is a relative movement between a fluid and a solid surface, whether externally around a body or internally in an enclosed passage, a boundary layer exists with viscous forces present in the layer of fluid close to the surface. Boundary layers can be either laminar or turbulent. A reasonable assessment of whether the boundary layer will be laminar or turbulent can be made by calculating the Reynolds number of the local flow conditions. So this is the condition of airflow of a airfoil. Airflow separating from a wind at a high angle of attack. So here you can observe the angle of attack to an airfoil. Flow separation or boundary layer separation is the detachment of the boundary layer from a surface into a wake. Separation occurs in flow, that is slowing down with pressure increasing after passing the thickest part of a streamlined body or passing through a widening passage. Flowing against an increasing pressure is known as flowing in a adverse pressure gradient. The boundary layer separates when it has traveled far enough in an adverse pressure gradient that the speed of the boundary layer relate, relative to the surface has stopped and reversed direction. The flow becomes detached from the surface and instead takes the forms of eddies and vortices. The fluid exerts a constant pressure on the surface once it has separated instead of a continually increasing pressure if still detached. In aerodynamics, flow separation results in reduced lift and increased pressure drag caused by the pressure differential between the front and rear surfaces of the object. It causes buffeting of aircraft structures and control surfaces. In internal passages, separation causes stalling and vibrations in machinery blading and increased losses, that is lower efficiency in inlets and compressors. Much effort and research has gone into the design of aerodynamic and hydrodynamic surface contours and added features which delay flow separation and keep the flow attached for as long as possible. Examples include the fur on a tennis ball, dimples on a golf ball, turbulators on a glider, which induce an early transition to turbulent flow, vortex generators on aircraft. So, boundary layer control. Here we can discuss about boundary layer control that refers to methods of controlling the behavior of fluid flow boundary layers. It may be desirable to reduce flow separation on fast vehicles to reduce the size of the wake, streamlining, which may reduce drag. Boundary layer separation is generally undesirable in aircraft, high lift coefficient systems, and jet engine intakes. Laminar flow produces less skin friction than turbulent, but a turbulent boundary layer transfers heat better. Turbulent boundary layers are more resistant to separation. So, on a cylinder, how can the boundary layer control will happen? In the case of a free stream flow past a cylinder, three methods may be employed to control the boundary layer separation that occurs due to the adverse pressure gradient. Rotation of the cylinder can reduce or eliminate the boundary layer that is formed on the side which is moving in the same direction as the free stream. The side moving against the flow also exhibits only partial separation of the boundary layer. Suction applied through a slit in the cylinder near a separation point can also delay the onset of separation by removing fluid particles that have been slowed in the boundary layer. Alternatively, fluid can be blown from a fade slit such that the slowed fluid is accelerated and thus the point of separation is delayed. Maintaining a laminar boundary layer on aircraft. Laminar flow airfoils were developed in the 1930s by shaping to maintain a favorable pressure gradient to prevent them becoming turbulent. Their low drag wind tunnel results led to them being used on aircraft such as the P-51 and B-24, but maintaining laminar flow required low levels of surface roughness and waviness, not routinely found in service. Crack states the tests on the P-51 airfoil done in the high-speed DVL wind tunnel in Berlin showed the laminar flow effect completely disappeared at real flight Reynolds numbers. Implementing laminar flow in high Reynolds number applications generally requires very smooth, wave-free surfaces, which can be difficult to produce and maintain. Maintaining laminar flow by controlling the pressure distribution on an airfoil is called natural laminar flow (NLF). So this is natural laminar flow and has been achieved by sailplane designers with great success. On swept wings, a favorable pressure gradient becomes destabilizing. Destabilizing due to cross flow and suction is necessary to control cross flow. Supplementing the effect of airfoil shaping with boundary layer suction is known as laminar flow control, that is LFC. The particular control method required for laminar control depends on Reynolds number and wing leading edge sweep. Reynolds number and wing leading edge sweep. Hybrid laminar flow control HLFC refers to swept wind technology in which LFC is applied only to the leading edge region of a swept wing and NLF after of that. NASA sponsored activities include NLF on engine nacelles and HLFC on wing upper surfaces and tail horizontal and vertical surfaces. At last, aircraft design. In aeronautical engineering, boundary layer control may be used to reduce parasitic drag and increase usable angle of attack. Fuselage mounted engine intakes are sometimes equipped with a splitter plate. Much research was conducted to study the lift performance enhancement due to suction for aerofoils in 1920s and 1930s at the Aerodynamic in Guatemala. An example of an aircraft with active boundary layer control in the Japanese seaplane Shinmaya US-1. This large four-engined aircraft was used for anti-submarine warfare (ASW) and search and rescue (SAR). It was capable of stall operation and very low air speeds. Its replacement in the SAR role and the Shinmoya US2 uses a similar system for its capability to fly at 50 knots. So, this is the topic about boundary layer control systems. Thank you.